This lecture will delve into the rich history and promising future of digital computing hardware. Digital computing hardware refers to the physical components and devices such as processors, memory modules, and input-output devices that are used to perform digital computations and process data in electronic systems. Understanding the trajectory of digital computing hardware offers profound insights into the evolution of technology, enabling us to grasp the remarkable progress achieved, learn valuable lessons from past endeavors, and anticipate the exciting developments yet to come. We'll explore pivotal moments in the history of processors, digital memory, networking, and business computers. Next, we'll overview 4 important laws describing how computer hardware is evolving. We will conclude with a discussion of the future of processors, digital memory, networking, and business computers. Understanding the history of digital computing hardware provides insights into the evolution of technology, allowing us to appreciate the progress made, learn from past successes and failures, and anticipate future developments in computing. The critical events in the evolution of the processing of instructions include semiconductors in the late 19th century. Observations of semiconductor behavior began in the late 19th century with the discovery of materials that exhibit unique electrical properties, conducting electricity better than insulators, but not as well as conductors. Transistors, 1947. The transistor, invented by William Shockley, John Bardeen, and Walter Brattain at Bell Labs in 1947, replaced bulky vacuum tubes and initiated the era of solid-state electronics. Integrated circuits, 1958. The integrated circuit was invented independently by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor in 1958. This breakthrough allowed for the miniaturization and integration of electronic components on a single semiconductor chip, revolutionizing the electronics industry. Silicon. Silicon emerged as the dominant material for semiconductor devices due to its abundance, reliability, and favorable electrical properties. Silicon-based technologies have fueled the rapid growth of the semiconductor industry since the mid-20th century. Semiconductor manufacturing is another facet of this history. Advances in semiconductor manufacturing techniques such as photolithography, chemical vapor deposition, and ion implantation have enabled the fabrication of increasingly smaller and more complex semiconductor devices. These manufacturing advances have pushed the limits of device miniaturization and improved the performance and functionality of electronic hardware. Here are some critical events in the evolution of digital memory, along with their respective dates. First is magnetic core memory, 1949. Developed by J. Forrester at MIT, magnetic core memory was the first reliable form of random access memory for computers. It used small magnetic rings or cores to store binary data and became widespread in early computers throughout the 1950s and 1960s. Second is dynamic random access memory. 1967, Robert Dennard, a researcher at IBM, invented the first dynamic RAM or DRAM cell. DRAM stores each bit of data as an electric charge in a capacitor, which requires periodic refreshing to maintain data integrity. DRAM became the dominant form of random access memory due to its high density and low cost. Third is erasable programmable read-only memory, or EEPROM, in 1971. Developed by Dov Froman at Intel, EEPROM was the first non-volatile memory that could be electrically programmed and erased using ultraviolet light. EEPROM was widely used in early microcomputers for storing firmware and BIOS data. BIOS stands for Basic Input-Output System and is the program a computer's microprocessor uses to start the computer system after it is powered on. Fourth is electrically erasable programmable read-only memory, or EEPROM, in 1978. Developed by George Perlegos at Intel, EEPROM allowed for electrical programming and erasing of data, eliminating the need for UV light. EEPROM provided a rewritable, non-volatile memory solution suitable for applications such as BIOS storage and data storage in embedded systems. Fifth is flash memory, 1980s. Fujio Masuoka, working at Toshiba, invented flash memory, a type of EEPROM that can be electrically erased and reprogrammed in blocks instead of individual bytes. Flash memory became the dominant non-volatile memory technology due to its high density, fast read-write speeds, and low power consumption. Sixth is NAND flash, late 1980s. Toshiba introduced NAND flash memory, a variation of flash memory optimized for high-density data storage. NAND flash is used in a wide range of consumer electronics, including USB flash drives, SSDs, and memory cards. And finally is 3D NAND in 2013. Samsung introduced 3D NAND technology, stacking memory cells vertically to increase storage density while reducing manufacturing costs. 3D NAND has enabled the continued advancement of solid-state drives with higher capacities and improved performance. A significant development in processing and memory was the floating gate MOSFET, 1967. Dewan Kang and Simon Sze at Bell Labs introduced the floating gate metal oxide semiconductor field effect transistor, or MOSFET. The floating gate can trap electrical charge, allowing for the storage of binary data without the need for power. In CPUs, which is the central processing unit, and other processing units, MOSFETs are used extensively in the construction of logic gates and other circuitry. They form the basis of the CMOS, or complementary metal oxide semiconductor technology, which is the most common technology used in modern microprocessors due to its low power consumption and high noise immunity. MOSFETs are also integral to various types of memory technologies. In dynamic random access memory, or DRAM, for example, each memory cell typically consists of one capacitor and one MOSFET, which stores a single bit of data. In flash memory, used in SSDs, USB drives, and other storage devices, MOSFETs are arranged in a grid to form floating gate transistors, which can trap or release electrons to represent binary data. The MOSFET is the foundation of modern digital integrated circuits. MOSFETs are widely used in digital electronics due to their low power consumption, high speed, and scalability. Here are some critical events in the evolution of networks, along with approximate dates. The telegraph, 1837. Samuel Morse demonstrated the telegraph, revolutionizing long-distance communication by transmitting electrical signals over wires using Morse code. The telephone, 1876. Alexander Graham Bell patented the telephone, enabling voice communication over electrical wires and laying the foundation for modern telecommunications. ARPANET, 1969. The Advanced Research Projects Agency network, funded by the U.S. Department of Defense, was created as a research project to develop a decentralized communication network. It is considered the precursor of the modern Internet. Next is the Transmission Control Protocol / Internet Protocol, or TCP/IP, in 1983. TCP/IP became the standard protocol suite for data transmission on ARPANET, providing the framework for the modern Internet and facilitating interoperability between different computer networks. Next is the commercialization of the Internet in the 1990s. The Internet transitioned from a government-funded research network to a commercialized global infrastructure, leading to the rapid expansion of online services, e-commerce, and social media platforms. Next is the World Wide Web in 1991. Tim Berners-Lee introduced the World Wide Web, a system for accessing and sharing information over the Internet using hypertext documents. This event popularized the Internet and made it accessible to a broader audience. Next is high-speed broadband in the 2000s. The widespread deployment of broadband technologies such as DSL, cable, and fiber optics enabled faster and more reliable internet access, supporting bandwidth-intensive applications and multimedia content. Next is social media platforms in the 2000s to 2010s. Platforms like Facebook, Twitter, and YouTube transformed the internet into an interactive and social space, facilitating user-generated content, online collaboration, and global networking. Next is mobile networks, the 2000s to the present. The advent of smartphones and mobile broadband technologies, including 3G, 4G, and now 5G, enabled ubiquitous internet connectivity, allowing users to access the internet anytime, anywhere. And finally is the Internet of Things, the 2010s to present. The proliferation of connected devices embedded with sensors and communication capabilities expanded the scope of networks, creating opportunities for smart homes, smart cities, and industrial automation. The evolution of business computers has been shaped by several critical events, including the development of key devices. Here are some of the significant milestones. First is the ENIAC, or Electric Numerical Integrator and Computer, in 1945. Developed by John Mauchly and Presper Eckert at the University of Pennsylvania, ENIAC was the world's first general-purpose electronic digital computer. It marked a significant advancement in computing technology and laid the foundation for subsequent developments in business computing. Next is the UNIVAC-1, Universal Automatic Computer, in 1951. Designed by Eckert and Mauchly's company, UNIVAC-1 was the first commercially available computer in the United States. It was widely used for business applications such as payroll processing, inventory management, and scientific calculations. Next is the IBM 1401 in 1951. The IBM 1401 data processing system became one of the most popular business computers of the 1960s. It featured high-speed processing, magnetic tape storage, and a wide range of input-output options, making it well-suited for data processing tasks in business environments. Next, the 1960s saw the emergence of mini-computers, smaller and less expensive alternatives to mainframe computers. Devices like the PDP-8 and PDP-11, introduced by Digital Equipment Corporation, became popular choices for business computing, offering flexibility and cost-effectiveness for smaller organizations. Next is IBM System 360 in 1964. IBM's System 360 family of mainframe computers represented a significant advancement in computer architecture and compatibility. It offered a range of models to suit different business needs, establishing IBM as a dominant force in the business computing market. Next is personal computers in the 1970s and 1980s. The introduction of personal computers, or PCs, included devices like the Apple II, IBM PC, and Commodore PET. These affordable and user-friendly computers brought computing power directly to businesses and individuals, revolutionizing office productivity and business processes. Next is enterprise resource planning systems in the 1990s. ERP systems such as SAP R/3 and Oracle applications emerged as comprehensive software solutions for managing various business functions, including finance, human resources, manufacturing, and supply chain management. These integrated systems provided businesses with greater efficiency and visibility across their operations. Finally is cloud computing in the 2000s. The advent of cloud computing technology transformed the way businesses access and manage computing resources. Cloud-based services, including software as a service, infrastructure as a service, and platform as a service, offered scalability, flexibility, and cost-effectiveness for businesses of all sizes. Several laws describe fundamental trends and patterns observed in various aspects of technology, such as computing, storage, internet bandwidth, and semiconductor manufacturing. Each law provides valuable insights into the rate of progress, growth, or change in a specific area of technology over time. Moore's law is an observation made by Gordon Moore, the co-founder of Intel Corporation, in 1965. It states that the number of transistors on a semiconductor chip doubles approximately every 2 years, while the cost of the chip remains constant or decreases. This observation has driven the rapid advancement of computing technology over several decades, leading to smaller, faster, and more powerful electronic devices. Kreider's law, proposed by Mark Kreider in 2005, describes the trend of increasing storage density in magnetic hard disk drives, or HDDs. It states that the storage density of HDDs doubles approximately every 13 months. This exponential increase in storage capacity has enabled the storage of larger amounts of data in smaller physical spaces, contributing to the growth of digital data storage and retrieval. Next is Nielsen's law of internet bandwidth, named after Jacob Nielsen. This law describes the trend of increasing average bandwidth of internet connections over time. It states that the average bandwidth of internet connections tends to increase by 50% annually. This observation reflects the ongoing improvements in internet infrastructure and the growing demand for higher data transfer rates to support multimedia content and online services. And finally is Rock's law, proposed by Arthur Rock. It describes the decreasing cost of semiconductor manufacturing over time. It states that the cost of semiconductor manufacturing facilities decreases by about half every 4 years. This observation highlights the continuous improvements in semiconductor manufacturing processes, leading to reductions in production costs and making electronic devices more affordable and accessible to consumers. Each of these laws will continue to influence the future of digital computing hardware. The future of semiconductors holds promise for continued miniaturization and increased performance. Technologies such as nanotechnology and quantum computing are expected to play a significant role in pushing the boundaries of semiconductor design. Nanotechnology enables the fabrication of smaller, more efficient transistors, while quantum computing offers the potential for quantum processors that can perform calculations at unprecedented speeds. Additionally, advancements in materials science, such as the development of novel materials like graphene and carbon nanotubes, hold potential for revolutionizing semiconductor manufacturing and unlocking new capabilities in computing and electronics. In the future, digital memory technologies are poised to evolve to meet the growing demand for higher capacity, faster access, and lower power consumption. Emerging technologies such as resistive random access memory, or RRAM, and phase change memory, PCM, offer the potential for non-volatile memory solutions with higher density and improved performance compared to traditional NAND flash memory. Furthermore, developments in 3D stacking and integration techniques are expected to enable the creation of memory architectures with increased bandwidth and reduced latency, paving the way for next-generation computing systems and data storage solutions. The future of networking is characterized by the convergence of various technologies aimed at delivering faster, more reliable, and more secure connectivity. Technologies such as 5G cellular networks and Wi-Fi 6/6E are poised to revolutionize wireless communication by providing higher data rates, lower latency, and improved network capacity. Moreover, advancements in software-defining networking, SDN, and network function virtualization, or NFV, are expected to enable great flexibility and programmability in network infrastructure, facilitating the deployment of dynamic and scalable network solutions. Additionally, the adoption of emerging technologies such as edge computing and quantum networking holds promise for distributed and secure network architectures capable of supporting the requirements of future applications and services. In the future, business computers are expected to continue evolving to meet the demands of increasingly complex and data-intensive workloads. Advancements in processor technology, such as the development of multi-core and heterogeneous architectures, will enable computers to deliver higher performance and efficiency for a wide range of applications. Furthermore, the integration of artificial intelligence and machine learning capabilities into business computers will enable more intelligent and adaptive systems capable of automating tasks, making predictions, and providing personalized experiences. Additionally, the proliferation of cloud computing and edge computing technologies will transform the way business computers are deployed and managed, enabling organizations to leverage scalable and distributed computing resources to meet their evolving needs. I hope you enjoyed this lecture on emerging computer hardware technologies. Thanks for watching.